Hi everyone, so we're going to pick up where we left off in a previous video to talk about something called the Dalton's Law of partial pressures. So Dalton's Law has to do with mixtures of gases. So previously we really have not been specific about what type of gas we talk about. It could be a mixture or it could be individual pure gases like just oxygen, for example, or just nitrogen. But in Dalton's law, we're specifically talking about mixture of gases. So an example of a mixture of gas that we're familiar with is air. Air contains about 78% nitrogen, 21% oxygen, and a bunch of other gases. And there's a certain way these mixtures behave that Dalton observed way back a couple of hundred years ago. And one of the things that's the most important is that when you have a mixture of gases, there's a certain total pressure associated with the gas. So for air, for example, it will be 1 atmosphere at sea level. Now it turns out that because it's a mixture of gases and all gases exert some pressure, the total gas pressure actually is the sum of the pressures from the individual gases. So we call these pressures from the individual gases partial pressures. So this equation is called the Dalton's Law of partial pressure. So if we have air, it would have been partial pressure of nitrogen plus partial pressure of oxygen, etc. So let's take a look at this problem with Dalton's Law. It says a mixture of helium, neon, and argon has a total pressure of 558 millimeters of mercury. And then if the partial pressure of helium is 341 and neon is 112, what's the partial pressure of argon? This is pretty much a straightforward Dalton's law problem. We know that we have 3 gases in our mixture, so our pressure total is going to be the sum of all those 3 gases. So we can write an equation that looks like this. And then what we don't know is the partial pressure of argon. I'm just rearranging my equation to solve for partial pressure of argon, which is going to be the total pressure minus the partial pressure of the other 2 gases. And plugging in those numbers, 558 minus 341 minus 112 would give me 105 millimeters of mercury as the partial pressure of argon. Notice that I don't need to convert the units of pressure to ATM, unlike when we're dealing with ideal gas problems, because in those problems we have the ideal gas constant that we have to worry about, but in this case we are not using R, so the unit can be in whatever units of pressure you like as long as they're consistent. The discussion about partial pressure that we just talked about is important because that goes into the way we typically collect gases in experiments. So this method that we typically use is something called the water displacement method in collecting gases. And the way it works is you would run a reaction that produces a gas, and that gas is allowed to come out from the container of the reaction, like a test tube in this case, right? And it's allowed to bubble up through water. So you can see that this tubing goes underwater and then goes up here. And basically, as the gas is produced, it's going to bubble up to the top, and because gases are less dense than liquid, it will go to the top, and after that it would fill up the space at the top. And the more gas you put in, the more this water level will get pushed down up to the amount of gas that you collect. Now the reason this is important and how it relates to Dalton's law is because when you collect this gas, you have not only the gas you collect, but also some water vapor that's already present originally on top of the liquid water. So in other words, the pressure of the gas that you have on top of the water is the sum of the pressure of the gas you collect plus the vapor pressure of water. Okay, so there's 2 things that add up to give you that total pressure. If somebody wants to know how much gas you actually collect, what you need to do is you measure the total pressure and you have to subtract out the pressure that comes just from the water vapor. So let's take a look at this problem where a gas is collected through water. So in this case, it says 193 milliliters of oxygen gas is collected over water when the atmospheric pressure was 762 millimeters of mercury, and then gives the temperature of the water. And the question is how many grams of oxygen were collected if the vapor pressure of water is 21.1. As I was saying earlier, the way you collect this is usually you have a tubing that runs to the top of some container that has water in it, and the gas is allowed to bubble up. I'm just going to use yellow here to illustrate the gas. So the gas is allowed to bubble up here to the top. Now, the issue, of course, is that the gas that you're producing, which is oxygen in this case, is not the only gas that's present, but you also have some water vapor, which I'm coloring as blue, that's already present because you have a liquid water in this case that's producing some vapor, okay? And so what we're going to need to do is we need to look at what the total pressure is, and the total pressure is what's given by that atmospheric pressure. The reason why that is because the way we collect this is typically by letting the outside pressure, which is the atmospheric pressure, equal to the inside pressure of the top of this container. So that pressure on the top right there. And so that 762 really corresponds to the total pressure. And so that total pressure is going to come from the pressure from the oxygen that's being collected plus the pressure from the water that's in the vapor state. So if you just want the oxygen, which you're going to need in order to figure out the mass of the oxygen, you're going to have to subtract the total pressure, which is 762, from the water pressure, which is 21.1, and that's in unit of torr. So the two units are not equal to each other, so they need to be converted, and you need to look up conversion factors between torr and millimeters of mercury, which happens to be the same, so 1 to 1. In other words, that's a fairly easy conversion to do. And so you end up getting 740.8 millimeters of mercury. Now the question itself is asking for the mass of oxygen. So if you think about mass, the way you can get to mass is you need to get the number moles, which is N, times the molar mass. So that means I first need to get my number moles. And in gases, we can always take a look at the ideal gas equation. And if we want to solve for N, we can divide both sides by RT. That would give us N equals PV over RT. The pressure is the important part. I have to use the pressure that I calculate just for the oxygen, which is 740.8 millimeters of mercury. And now, since I do have R here in my calculation, I have to convert this to ATM. So remembering or looking up the conversion factor between ATM and millimeters of mercury, which is that. The volume is 193 milliliters of oxygen. That's what we're given originally. So I'm going to convert that to liters. Remember that for R, I have to use liters as my volume unit. And then I'm going to divide that by R, which has that value and those units. And then lastly, temperature. The temperature that was given was 23 degrees Celsius with a temperature of water, which we assume is going to be the same as the temperature of the gas. So 23 plus 273 because it has to be in Kelvin. And this ends up giving us 0.007741 moles of gas. So to get the actual mass, I will take the number of moles and multiply that by the molar mass of oxygen, which is 32. And that would give me 0.248 grams. The last topic I want to talk about in this gas chapter is really doing stoichiometry calculations with reactions where gases are involved. The main new thing here about reactions involving gases is that we have the ideal gas equation, PV equals nRT, where N, of course, stands for the number of moles. We know that in stoichiometry, typically we have to convert our quantities into number of moles. Right? In previous stoichiometry situations, we would take mass and convert them to moles. So now what we can do is if we're dealing with gases, we can also convert from volume, from pressure into number of moles using the ideal gas equation. So I'll show you how to do this in a couple of different examples. The rest of the steps are really similar to other stoichiometry situations. You might have to figure out limiting reactants. You might have to figure out yields. So let's take a look at a problem of gas stoichiometry. Here it says you are asked to find the number of grams of magnesium oxide when 14.8 liter of oxygen measured measured at STP completely reacts with magnesium metal. Just like any stoichiometry problem, the first thing is to write the balanced chemical equation. So we have reaction between magnesium and oxygen to produce magnesium oxide. You balance the equation, it should look like that. What we're told is we have 14.8 liter of oxygen. This is in excess, so clearly oxygen is the limiting reactant. So that means to find the magnesium oxide, what we need to do is convert our oxygen to number of moles and then use the mole-to-mole relationship with magnesium oxide and then afterwards to calculate the mass using the molar mass. So we can actually do that in one shot. We start with 14.8 liter oxygen. Now the key word here is STP. If you remember, STP means that at 1 mole of any gas, including the oxygen here, we're going to have 22.4 liter. And so that converts my volume of oxygen to number of moles. And then I can use my balance equation to convert the oxygen to the magnesium oxide, which is a 2-to-1 relationship, and then multiply by the molar mass of MgO, which is 40.3044 grams per mole. And all these units cancel away, giving us in the end the mass of magnesium oxide. This gives us 53.3 grams.